This is problem 3 on practice exam 2 of chapter 2 in the book Problem Solving with Differential and Integral Calculus. We have water draining from a tub. Starts off with 1,000 liters of water in the tub, ends up with no water in the tub after 1,000 seconds. We have to go from part A through H in this problem, so let's ignore everything else but part A. Let's focus on part A and we'll worry about the rest later. Part A, estimate the initial flow rate of water out of the tub by drawing a tangent line at t equals 0, getting the slope. We have a plot of water in the tub versus time. So the slope of that line, dV, volume of water in the tub, dt, is the drain rate. So let's draw a good tangent line at t equals 0, and let's be bold, we draw it way across. Draw a long line. Don't worry about going to negative times, that's okay. We just want to get a good tangent line. So the rise is pretty easy. It goes from 0 to 1,000. It's going down. So the rise is negative 1,000. And the run looks like 500 seconds, right? Pretty straightforward. The slope is minus 1,000 liters in 500 seconds, and I can do that in my head. Minus 2 liters per second. That's the initial drain rate of water from the tub. On to part B. Part B asks for the same thing at 200 seconds. What's the drain rate? So let's label the point, and let's draw a good tangent line at 200 seconds. 900, that's 1,000, that's about 960. So the rise is minus 960, and the run is nice, it's 600 seconds. So the slope is minus 960 liters in 900 seconds. That's the rate at 200 seconds. So minus 1.6 liters per second, and we can see that the drain rate is a little bit less at 200 seconds than it is initially. On to part C. Part C asks for the drain rate at 800 seconds. So let's draw a good tangent line, put a dot there, there's the tangent line. You gotta eyeball this. There's 300, that's 400, that's 360 something, minus 360. The run, it's hard to tell. I'm gonna guess 900. So the slope is minus 360 liters. It drops 360 liters, 900 seconds. That's the rate, minus 0.04. This is the rate only at 800. Of course, it's not the rate at 200. It's the rate at 800 seconds. On to part D. Using the equation of the tangent line, calculate how much water flows out of the tub in 5 seconds at 0. We know what the flow rate is at 0. We measured it. We estimated it with the tangent line. It's 2 liters per second out. And if that 2 liters per second is constant over 5 seconds, which it's very close to, 5 seconds is way in here. So it's going to be pretty straight over the first 5 seconds. So if it drains at 2 liters per second for 5 seconds, how much comes out? 10 liters, right? About 10 liters. On to part E. So now it asks for the same thing from 200 to 205 seconds. How much comes out? Note that we're using deltas here. Delta, we want to know what delta V is. Delta T is 5 seconds. And we know what the rate is. It's 1.6 liters per second at 200 per second, at 200 seconds. So we have this equation, delta V minus 1.6 liters per second delta T. We stick in 5 seconds there, and we get minus 8 liters. So the flow rate's dropping, right? Makes sense. On to part F. Part F says, using the equations of the tangent line we calculated in part B, estimate the volume of water that flows out of the tub from 800 seconds to 805 seconds. So from here to here, what's delta V? So we're going to assume the line is straight from 800 to 805 seconds, and we're going to use the drain rate at 800 seconds. We estimated it to be 0.4 liters per second at 800 seconds with the tangent line. If it drains at 0.4 liters per second for 5 seconds, we lost 2 liters. So the drain rate is pretty slow when you get near the end. On to part G. The equation of the line is this. This is the normal equation. 0.001 liters per second squared times t minus 1,000 seconds quantity squared. If you plug this into a graphing program, you'll get that curve. Use differential calculus to get the relationship for dv in terms of t and dt. This is real calculus going on here. It's a great opportunity. We're taking a derivative of both sides of the equation, so we understand what's going on here. So the equation of the line itself is the normal equation, and we're going to shift time by a little bit, dt. We're not using deltas anymore, and the resulting change in volume is dv. So we're going to change the time from t to t plus dt, and the volume of the tub changes by dv. So here's our equation. V plus dv is t plus dt. Right? It's a little bit time later, and dv changed. That's the volume change. So we're going to focus only on this term over here, in parentheses, the squared term, this one right here, because that's going to be a pain. We have to square that, and there's 3 terms in it. So we're going to take it slowly, leave off that constant term, just focus on that term. So multiplying this out, we get this. And this is dt squared. It's nonlinear. We can throw it away. It's infinitesimal compared to 2t dt. So we drop that, and I'm going to regroup the remaining 5 terms so it looks like the volume, so we can extract the volume. So I put the t squared with the 200 seconds t and the 1,000 seconds squared. That's in the square brackets, and then we have the 2 terms with dt in them, minus 2,000 seconds dt, and then over here, a 2t dt. So if we add in the leading constant, which we left off, this 1,000th of a liter per second squared, put it in here, that's the volume V. But we're going to take it slowly, recap what's going on, and get rid of this graph so we can have more space. So we started with that. We multiplied out the squared term, we dropped the dt squared term, and we rearranged it so it looks like this. And if you substitute it back in, it looks like this. So I put the constant back in, I put the v and the dv. Now this term right here in square brackets times this, that's just v. That's just v. Here's v. Remember what v was? It's that. So if we square out the t minus 1,000 seconds, we get t squared minus 2t times 1,000 times t. That's this. And then we have the last term, the last squared, 1,000 seconds squared. So this is v. And there's a v right there. We can subtract v from both sides. And we get dv, expression for dv. It's 1,000 or 1,000th of a liter per second squared times these 2 terms right here. We want the slope, which is dv dt, so we just divide both sides by dt. And what I did right here is I switched the order of this. I got minus 2,000 seconds plus 2t, and I just wrote it as 2t minus 2,000 seconds. Should make sense. And that's the slope at any t. This is differential calculus, real differential calculus. So part H, finally, use this expression for the slope to check our estimates at 0, 200, and 800 that we got with the tangent line. So here's the equation of the slope that we just derived. If we want to know the slope at 0 seconds, we stick in 0 for t. We just plug it in. So here's t right here. We stick in 0, and we get minus 2,000 seconds times that. Minus 2,000 seconds times 1,000th of a liter per second squared. Minus 2 liters per second. And if you remember, that was the initial slope we got. The drain rate in the beginning with the tangent line, we estimated it to be negative 2 liters per second. Now let's do it at 200 seconds. It's the same equation. That's the beauty of the derivative. We don't have to do it again. We have to draw a tangent line everywhere we want the slope, but we just have one equation. We just plug in 200 seconds here. 2 times 200 is 400. 400 minus 2,000 is 1,600, minus 1,600. So minus 1,600 times 1,000th is 1.6 liters per second, and it's negative, the drain rate. And that's what we got at 200 seconds. The slope at 200 seconds is minus 1.6 liters per second. Finally, we go to 800 seconds. We stick it in. There's the equation. If you stick in 800, you get 1,600 minus 2,000, which is minus 400. Minus 400 seconds times 1,000th of a liter per second is minus 0.4 liters per second. And if you remember, that's the slope we got at 800 seconds. If you are not completely lost, congratulations.